Thanks for attending today's webinar. The topic today is reducing CFD simulation time with TotalCAE and AWS and Hpc6a instances powered by third generation AMD EPYC processors. I'm excited today that we have Erica Boeing, CEO of Accelerate Wind, to talk about her company's experience going from a workstation environment to a cloud computing environment to speed up their simulation results. I'll give a little bit of a talk about TotalCAE and a demo of the kind of environment that Accelerate Wind used. Ninesh Degraskar, from a senior HPC partner solutions architect with AWS, will be talking about all of the AWS technology that's being under the hood that drives all this. And then Rick Knuckle, AMD field application here, will go into a deeper dive on the processors that we're using to get these kinds of results. So with that, I'm going to pass it along to Erica Boeing.
Hi, thanks, Rod. Hi guys, I'm Erica Boeing, founder and CEO of Accelerate Wind, and we're an early stage startup company that's developing affordable wind turbines for commercial buildings. So I'll dive in and tell you a little bit about us and then specifically the computing problems that we were able to solve with TotalCAE. So zooming out to a high level, Accelerate Wind came from a realization that the renewables industry was just thriving. Rooftop solar is a $9 billion market in the US, and it's one that's growing significantly. But there's also a problem, and that's that most solar installers were installing on commercial buildings, maxing out the entire roof capacity, and still only able to meet maybe 25 to 40% of a building's overall energy demand. Which meant that there's a huge opportunity that was being missed. And what we saw as the opportunity was that wind energy actually has the potential to add on an average of 25% additional energy generation on top of solar, and sometimes even double that capacity depending on where you're at in the country. And so we wanted to capitalize on that opportunity, but realized that the main problem was that existing rooftop wind turbines just weren't profitable. So the average cost of a rooftop wind turbine today was about $5.48 per watt, meaning that the payback was often longer than the lifetime. And the thing that really enabled solar to take off was being able to be cost competitive with other energy sources and something that could be paid back quickly by customers. And when we looked at it, we realized that the problem with existing rooftop wind was a mix of hardware costs and soft costs, so things like customer acquisition, installation, and permitting, like you can see on this slide. So we had to tackle that holistically. And that's exactly what we've done with our company over the last 4 years. We've developed a turbine that is designed to reduce cost in 3 ways. On the soft cost side, we are able to reduce costs by selling through solar installers. And then on the technical side, we use edge of roof wind capture and our patent pending powertrain architecture to reduce costs. And what this lets us do is take that cost from $5.48 per watt today all the way down to about $2 per watt, which is a 4 to 6 year payback time. That's what customers are used to with solar, and will let us scale in the market. Now, these 3 approaches probably don't mean a lot to you yet, so I can talk through each of those on the next slides. So the first thing we do, I mentioned, is we've designed our turbines to be able to be installed by solar installers and sold through solar installers and installed alongside solar. So our turbines go on the edge of the roof, where we estimate there's about 2,500 miles of unused roof edge space alongside solar installs in the US today. And solar can still go on the rest of the roof, and buildings are able to move closer to net energy. This creates an extra revenue stream for solar installers, lets building owners generate more electricity, and lets us use the fact that solar installers are already really good at lowering costs for things like customer acquisition, installation, and permitting. So we don't have to develop that expertise on our team. The second thing that we're doing is we've spent a lot of time refining our powertrain to use all commercial off-the-shelf components, and we have a patent pending powertrain architecture that lets us cut powertrain costs to about 50% of what they would be otherwise. And then what we're really here to talk about today is our third cost reduction strategy, which is the fact that we leverage the fact that winds are naturally faster at the edges of roofs than other parts of the roof. You can see this in the image here on the left, where we have a computational fluid dynamics model of wind going over a typical roof, and all of the wind that hits the vertical face of the building speeds up as it goes over the edge. But the problem is that you really only get the speed up in orange on that picture on the left, which is far above the roof. You'd need a tall tower to capture it, which would be ugly. It would be expensive and not really make a lot of sense. So Accelerate Wind's core technology has all been about how do we draw that faster wind speed down right to the edge of the roof so that we can prevent flow separation and produce meaningful, affordable power right at the edge. And so that's what you can see on the image on the right is we are using modern airfoil shapes. It's taken us thousands of CFD iterations to figure out what shapes work the best so that we can draw that faster wind speed down to the edge, produce power right at the edge, leave space for solar on the rest of the roof, and develop a system that's cost effective. And with our system, we're estimating that we can produce about 3 times more power compared to competitive systems. And also it looks pretty cool. So this is actually what it looks like on the office building that we sit in right now. We've worked a lot with architects and community members to get feedback on how the turbine looks and how communities will respond to it so that it can be something that adds to the aesthetic of a building. We've also tested our system at Argonne National Lab. A lot of the work that we've done over the past several years has been in partnership with them, and we've had a prototype unit running on the roof there for the last 2 years. I guess the last thing that I'll say at a high level is that what our technology enables us to do is create an add-on market to existing and new solar installs. So in the US, that's a $1.8 billion market. Globally, that's a $21 billion market. And really just leveraging a lot of the good work that's already been done with solar and adding another energy source there. So we're just getting to the phase where we've proven out a lot of our core IP and are getting ready to install pilots and scale up, and are excited to tackle that market. One of the big things that has been preventing us from really refining our tech past the core IP is that in order to model all of the different scenarios that we'll see in the real world, we need to run really large CFD simulations. So what you can see here on this image is actually kind of a small simulation for us, where we model a building with a bounding box of about 120 meters by 350 meters, 5 to 20 million cells. If we really want to do this right, a lot of times we can have a bounding box that's several kilometers wide, and then we need to be able to mesh that entire bounding box, but then also be able to mesh just a few centimeters at the spoiler system that guides the wind over the edge of the roof. So these simulations can take a lot of time, and we've been able to do a lot of core simulations to prove out the core IP, but then are getting into the phase where we need to move more into the real world. And so we've been running this. We got set up with ANSYS Fluent a few years ago, working with Boston Engineering and the ANSYS startup program, and have had a lot of success. We've been running all of our simulations on-prem with several workstations. The biggest one's a 32-core workstation with 128 gigs of RAM. We also have a few 16-core and 12-core systems. And we've been able to run all the iterations we needed for our core IP with that. But we're starting to hit a point where we could only test a few parameters at a time. If we wanted to sweep through and really optimize the technology, it could take days to weeks to do an optimization, even on like wind coming from different angles or wind from different speeds and how it reacts to that. And there's a lot more that we want to be able to test. We wanted to be able to test everything we were running was at steady state, because transient simulations just took too long, and there's definitely some transient effects that we need to be able to measure. We want to be able to measure how different building shapes affect the flow, how obstacles such as trees and cars and other buildings will affect the flow in a particular location? Are there other shapes that we could use to optimize the system that we haven't been able to run through enough simulation to fully test? We're just kind of hitting our limit where we've done all of the modeling we could do with the system. And also, we're running into bottlenecks where on our workstations, we had to either be solving or post-processing. The computer couldn't handle both at the same time. And so that would leave a lot of waiting time while our CFD people were waiting for several hours for the solution to solve. And so we approached TotalCAE to help us with this. We're a team of mechanical engineers and aren't experts on this, and they were able to spin us up on their system using AWS and the Hpc6a units to run a model on significantly more cores with a lot less time. So actually, we ran it about 2 weeks ago. We started using the system for the first time and saw that with our HPC packs that gave us access to a 384 core unit, we were able to cut run times down to about 1/15 of what they were before. So something that probably would have taken us months to run before, we've been able to run about 50 iterations in the past week. And we're still kind of in spin up mode on the project as well. We've been using their system for about 2 weeks now. So I think it'll only get faster as we kind of optimize our processes. This is a huge improvement for us. And most importantly, we're a bunch of mechanical engineers. We are not AWS experts. We don't know how to set things up on the cloud and didn't really want to get that expertise onto our team. And so they were able to set things up in a way that was really seamless for us. They were able to handle all of the work with AWS, and really we just were presented with a solution that looked like our workstation, what we're used to using, and we could spin up pretty quickly. And we also have a lot of options for what the number of cores that we can run on. So first we tested with a 96 core node, just running one node, and that was able to cut our time down from about 4 hours per run to 36 minutes or so. And then with 192 cores, we were able to cut it down to less than 20 minutes. And then if we want to run full speed at 384 cores, then that was about an 11-minute run. And then we can sweep through a lot of different parameters if we're doing that. There's a little bit of a cost trade-off there. So I think it's most cost effective for us to run at 96 cores. And for a lot of things that we're doing, that's fast enough. But we've had a few things that we're trying to get done over the past few weeks, and it's been nice to have the option to run faster so that we can just hit some of our milestones faster. Spin up was really easy, as I mentioned. One of the things that our team was worried about was if the interface would look different than what we're used to. And with TotalCAE's platform, that's one of the reasons we decided to go this direction, is we actually are able to use a virtual desktop where Workbench looks exactly like it does for us on our on-prem machines. We can run things through journal files if we want to, but we don't have to, and there's no need for any kind of command line control. It's really, really easy for our team to just continue to do what they were doing before. Interface has been great to be able to monitor the status of everything that's going on, and turn the nodes on and off automatically so that we don't need to spend a lot of time watching the computer. And we can see we have 2 ANSYS licenses right now, and so seeing the availability of the ANSYS licenses in our HPC packs and monitoring that was pretty seamless and easy, and tracking the job times has let us figure out what the best, I guess, dollar per core simulation is for us to run. Something that we were a little bit worried about when we got into it was the billing system, and just there's a lot of different costs between the cost to use the AWS cores and then some of the overhead costs using the desktop, but the billing system is really easy to see costing us and how we want to optimize for that. And the team's also been really great to work through that process with us and kind of walk us through what we need to be thinking about. So it's been going really well. I'm super excited about all of the development that we'll be able to accelerate with using the system. I think I wish we would have done it sooner. Some of the things that our team's been hung up on for a while, we've been able to solve really, really quickly. And I think we'll get a lot of the use of this going forward. So yeah, thank you. And thanks to the TotalCAE and AWS team for helping us out. And we're looking forward to bringing our technology to the world faster.
All right, thanks, Erica. That was a fantastic presentation. Yeah, we really enjoy. I mean, that's what we live here for, is to help customers, get more work done with less effort. And so glad to see that you had a lot of successes, and look forward to keep working with you on the journey here. So what TotalCAE basically does, if you haven't heard of it before, is help customers like Accelerate Win, adopt high performance computing. So we're an AWS HPC competency partner, and we combine that AWS infrastructure and hundreds of apps, not just ANSYS, but any major app you're going to root. We have over hundreds of apps that we support on the cloud. Then we make a simple to use interface so that you can focus on engineering and not IT. Everything you need is included, just simple clicks of a button, which we'll show here momentarily. So you don't have to be an IT expert, nor have to have a whole paradigm shift just to take advantage of high performance computing. And then we have a support team that's going to help you out, like we help with Accelerate. We have global support, 1-hour response times. Make sure that you're able to hit your deadlines and get up to speed quickly so that you can take advantage of the system. So the challenge that we really are here to solve is to help clients that want to adopt high performance computing, but it's too much of a leap to go from a workstation to that. It can be a bit daunting. And so we are here to help you adopt that with minimal IT knowledge and effort. We're going to be able to take care of everything for you. And when you go to a distributed environment, there can be a lot of things that can go wrong. There's a lot of complexity in these environments. It can be deceivingly simple when you look at the demo or see what's happening. But under the hood, if there was something to go wrong, you always have one contact, TotalCAE. We're going to figure out, is it a cloud issue or an application issue, middleware, scheduler, Linux? I mean, there's just a lot of different pieces that could go wrong. You just have one number to call, one email to send. We're going to help debug that, keep your engineers working online, help you coordinate tickets with the ISV in case there's a CA application issue. And so with that, I think maybe we could show a quick demo. While we have a batch-oriented system where you just upload your model, choose your application, and push the button, we have other methods to submit, including command line and desktop, which we'll show here right now, so you can just see it for yourself. So just give me one moment. All right, so we are here in the TotalCAE portal. And when you first log in, what you're going to see is your applications on the left, whatever ones that you use at your company. And then you're simply going to upload your model, and it's just a simple button. You'll see like a familiar looking tree here, and I can make a directory inside of here let me just call it test directory. And then from this test directory, you can upload, models if you'd like to upload. In this case, I have this is going to be for Fluent. So I have a case and data case file, a journal file right here. Those are going to upload. I can simply then select my journal file, pick the number of cores. I'm going to choose the Hpc6a 48 extra large instances. These are the AMD instances that Rick will talk about in a little bit that Accelerate Win is running on. And then I set a little time limit to make sure maybe maybe the solution doesn't converge, has some kind of issue. I want to be able to cap the costs. So the most this simulation could cost me is $5.76. And it gives me the kind of approximate rate, so I have an idea of how much the simulation may cost me. And I push the button, and then it's going to show the list of jobs. Now it runs a scheduler, and you can we calculate the number of ANSYS licensing you need, so that if there's not enough, it won't power on. And then you can reorder the queue. If you maybe have a hot job that needs that licensing before other jobs, you can reorder this, cancel jobs, control all that. But once you submit the job, it's going to go out, it's going to power on some virtual capacity. We have kind of a visual representation of these, these cloud instances that will be running to calculate the job. And as it's running, it'll power on, solve the job, power it off, and then you're just paying for that time that you used, and that's kind of it. Now, what Erica's team liked is they use this desktop tab to launch a cloud desktop. So when you turn on the desktop, it costs about $1.34 an hour, and it'll bill it to a project. And then you can go ahead and get a little URL, which I've logged into here, and then you could launch Workbench kind of like you're used to. So when you're in ANSYS Workbench to submit to the cloud solution, it's very much like you do on your workstation. You just click the update button, and then the same thing happens. The compute nodes will start turning on. They will then calculate the job once it's running, and then it will download the results back to this cloud workstation, and you'll be able to post-process it right here on the cloud workstation. Now you could stay all inside of ANSYS Workbench. You could even monitor the job. I can click on it here. I know I never need to go out and to another system if I didn't want to, but still it's kind of handy to have the TotalCAE for just reviewing what's going on. I could actually see that ANSYS job running here in the system. I can see the directory if I wanted to go, if something's going wrong, I could look at the files as they're running and look at the transcript. And I can kind of see what nodes it's allocated for this Workbench job. Now, in addition, there is a command line way to submit because the portal is nice, and so is Workbench. But if you have maybe you have an application that's hundreds of maybe load cases where you have just hundreds of directories, and clicking on a lot of stuff is not going to be very efficient. Well, we have a command line version of the portal called tsubmit, and every option that you have in the portal is available at a command line. You can pick queues, you can pick jobs, cores, when do you want it to run, comments. And it's quite easy. You can type tsubmit, the application, pick the model, the number of cores of the queue, hit enter, and it will submit a job for you. And with very minimal knowledge of just how you're doing some loops, you can easily loop through hundreds of directories, submit jobs rapid fire, and be able to do like designs of experiments, or even integrate with third-party tools, DOE tools that sweep the design space, and easily be able to utilize the cloud system because it behaves just like application vendors would expect. We also have that billing system that Erica mentioned. Hey, it's many people want to be able to see where is their simulation dollars going so they can more optimize how they're using the system to stretch their simulation budget. So in this case, I can see all of my jobs, how much did they consume, how much did my cloud desktop usage cost. You're able to put caps on users and projects and build them to various projects. You can also just hit this export button and export all of this to Excel if you wanted to, slice and dice it in Excel. You'll have all the details, so you could really analyze your bill on a job in a simulation kind of perspective, which is a lot easier to understand versus maybe looking at a standard cloud bill behind the scenes. You're going to be able to trace everything to a particular simulation, a particular user on a particular project. And this billing system comes kind of baked in, and you can control and manage all your costs through a simple to use web interface. Now, the final thing that we include is a bunch of analytics. So you can kind of see how much are you utilizing the cloud capability that you have. Many customers are license bound, so we also will do license calculation. How much are you using your licensing? So you can see, how often are you pending on licensing? Maybe you need additional HPC packs or additional other types of licensing to help you run on the cloud more. It'll give you metrics on average job sizes. How long are you waiting for jobs? Who's using what? Storage, how much of the cloud storage are you utilizing? How much are you leaving there that's very old so you can help clean up cloud storage? Are you using EFA? And then one thing that's kind of handy, if you look at these jobs that are running, once they power off, if your job didn't run, you may want to know like what happened. Did I run out of memory? Once the node turns off, it's hard to go back and see necessarily what happened. But with this integrated analytics, we can go back and we could dial right into what was happening, at that time. And so even though the node is just turned off, I could go back and say, okay, did it run out of memory? No, I had plenty of memory. Or maybe it did run out of memory. And then you'll go back and choose a different instance type that has more memory for your job, or maybe you reduce the mesh or whatever you need to do to get the memory footprint down. So that, in its nutshell, is a high-level whirlwind of the TotalCAE platform. This is all running on AWS, and its goal is to make it extremely easy for you to use without having to learn a lot of IT knowledge. So with that, I'm going to bring it back to the presentation. All right, next I'd like to introduce Yanesh Degraskar, Senior HPC Partner Solutions Architect, to tell you more about all the fantastic AWS technology under the hood that's being driven by the solution.
Thank you, Rod, for the introduction, and then thanks for the demo as well. I mean, it was very helpful. The results Erica showed were really fascinating, and personally, having worked in the wind industry for more than a decade on running these high fidelity CFD models on wind farms, it was pretty great to see, and got me a bit nostalgic as well. I'd like to talk briefly about the common challenges that CFD or HPC engineers typically face on premises. The simulation jobs often end up stuck in the queue, waiting for the job at the top of the queue to finish, so that job can start running. In that situation, engineers often end up reaching to the cluster admin, asking to increase the priority of their job. Now, in most of the cases, right, all jobs are high priority for important customers. The other common issue is that many users often end up running out of disk space, and then engineers keep asking for terabytes of additional storage. This can really impact the number of simulation workloads that can be run on a daily or weekly basis until that disk space is cleared. I've been a CFD engineer myself and been in these situations multiple times. On-premises hardware often means that engineers persist with outdated technology and are not able to take advantage of the latest developments in processors or storage or networking technologies. That often translates to a fixed simulation time, as the solver, the underlying solver, which SANS is Fluent in this case, that you are running, is not able to take full advantage of the latest technologies or state-of-the-art technology that is in the processors or storage, right? So with this, what happens is to speed up the simulations, often engineers end up reducing the cell count or change model parameters so as to fit the problem size to the available compute capacity. This is similar to what Erica mentioned as well as one of her challenges her team saw. And so this is not ideal to innovation, right? Another issue that I think greatly impacts productivity and time to results is the reduced collaboration on-premises clusters. This translates to, again, reduced innovation. Again, for example, let's say if a software license budget is fixed or hardware budget is fixed, then that limits the number of simulations that can be run simultaneously, and at the end affects the productivity. So in this presentation, I plan to highlight how TotalCAE platform on AWS Cloud can help you overcome these challenges or bottlenecks and have a streamlined process of completing your HPC workloads. The image on the left here represents a typical on-premises data center scenario. You have finite machines, finite number of queues, and that potentially resulting in engineering bottlenecks due to this fixed capacity. Now, pre-cloud, this was acceptable. I've been an engineer and have managed with on-premises queues and infrastructure for a really long time. Whereas today, the needs of compute are much more complex. each design workload can have different requirements in terms of CPU performance or memory specs, storage or networking. Take an example of CFD simulations. The CFD simulations are these tightly coupled compute and networking heavy simulations. On the other hand, finite element analysis simulations, they would require, which would involve, let's say, large matrix operations. They would require more memory or storage or instant access to storage. So on the right here is the representation of capacity in AWS cloud. Now each job can be elastically scaled to run on any number of cores, and there can be multiple queues running multiple workloads at the same time. Now this scenario enables engineers to fit their compute to their original problem size or the workload size and continue the innovation pace. Next slide, please. This map here shows the number of regions AWS has all over the world. We have 26 global regions and 84 availability zones. Each availability zone has at least one data center full of servers, and add all that together, you'll get a truly global infrastructure where we're adding capacity every single day. Again, taking a reference to a traditional data center scenario where your HPC cluster, let's say, is located in a single place. If your company's engineers are located globally, so they'll typically have to face challenges in getting an instant access to a job queue, or there could be even latency issues when transferring these huge flow fields or data from the cluster. I recall logging in at night multiple times in order to start the transfer of CFD case files and then getting them back by next morning. The advantage of this global infrastructure is that now engineers or teams, let's say in India or Japan or Australia, can use the TotalCAE platform and access the same resources, deploy same clusters in their nearest regions, and run the workloads. Next slide. So as the customers choose to run these various workloads with different needs, AWS innovates on behalf of its customers in order to give them the platform to meet those needs. We have a wide choice of products that can be catered to any workloads you wish to run. You can use our latest generation of GPU instances that contain NVIDIA A100 GPUs for running specialized workloads. There are dedicated machine learning focused instances to accelerate your machine learning workloads. You can run compute intensive workloads on our latest generation of AMD instances, such as the Hpc6a, which is focus of today's webinar, or Intel or AWS made Graviton instances. And you can add options such as high networking, elastic block storage, FSX for Lustre to go with all that. So as all this comes together, we have more than 500 instance types to support virtually every workload and business need, and we plan to continue adding more. So with that, I'll pass it on to Rick. Thank you.
All right, wonderful. Well, thank you, Dinesh and Rod. Erica, I want to commend you. Wonderful presentation and a tremendous example of how upstart innovative companies are leveraging the power of the cloud for high performance computing. So the way to think about this is AMD, one of the leading chip manufacturers in the world, and with our recent acquisition of Xilinx, now the largest market cap semiconductor company in the world. We offer a lot of instances in conjunction with our work with AWS. We are the compute engine under the hood for a lot of different applications, but most importantly here with Hpc6a, this is the first purpose-built compute instance that AMD has delivered to AWS. AMD has a very strategic focus on HPC. We do a lot of work to optimize the performance of codes like Fluent and others that are supported by TotalCAE on AWS and Hpc6a, and we're really leading the industry when it comes to the price performance of these cloud-based compute instances. Next slide, please. So a little bit more about the Hpc6a instance. Like I said, it was purposely designed and built in conjunction with AWS engineers. So we did a lot of work on the design and optimization. It's a dual socket machine, so there's 96 cores per instance. We don't use the simultaneous multi-threading. Healthy dose of RAM with up to 4 gig per core per RAM, and we take advantage of AWS's 100 gig elastic fabric adapter network dedicated for the MPI and Lustre traffic that is needed to support a wide variety of the tightly coupled HPC workloads that we see, along with low latency and high bandwidth. These are optimum metrics for performing exceptionally well on these type of workloads. You can see the pricing over here in the corner. It's very aggressive for the on-demand use of Hpc6a, and if you know that you're going to have a substantial amount of work over a larger period of time, you can get great savings associated with a reserved instance. Right now, the availability of Hpc6a is starting out in a couple different regions, and then with a single availability zone, but this will be rapidly expanded as the rollout of the new compute instance continues. An example of why we talk a lot about price performance, this is a classic benchmark done by the folks with ANSYS. It's the Fluent F1 race car. It's a 140 million cell model, and you can see that the Hpc6a is demarked here by the blue line over other alternative choices available on AWS. But with the pricing that we're able to roll out with AWS and the performance, you can see that for nearly identical performance in terms of an ANSYS, their metric or performance of runs per day, you're getting nearly 30% saving for near identical performance. There's a link to a great video done by the folks from AWS on the use of Hpc6a with a wide variety of ISV codes that's there on a YouTube channel. And I strongly encourage you to take a peek at that. You'll get a better sense of how well we perform across a wide variety of ISV software for CAE HPC. Next slide. Scaling is also an important piece of the equation here, and we're very pleased that we get highly linear scalability with respect to when you scale up to solve larger problems. And so here's a wide, 4 different examples of traditional Fluent benchmarks, and you can see that single node, double node, 4 nodes, 8 nodes, 16 nodes, as we scale up, you'll get 16x the performance at 16 nodes. So Hpc6a, gives a great dose of scalability to these codes when run on AWS. And that's important because when you scale linearly, you can significantly cut the time to solution, which Erica so aptly demonstrated in her presentation.
All right, well, thanks a lot, Rick, for the details there on the Hpc6a. It did have exciting benefits, and that scalability was definitely proven with a real-world model there with Accelerate Win. So I just wanted to wrap up here and say, if you are interested in getting these results that we showed that we have with Accelerate Win today, you could register here at the URL below, and qualified attendees will get a $250 cloud credit to actually try to stand this up in your environment, so you can give it a test drive and see these results for yourself with your applications and your models on AWS. So with that being said, I think we might take some of the chats that occurred during the call here. Now, if you're watching this recorded, you can enter into the chat. It will email us even after the recording questions, and we'll get back to you on those questions. But here on the live event, we'll take a couple that I see here. We're going to say, so one question was, do you sell licensing or is the licensing included? So the a CA licensing is, we don't sell, TotalCAE does not sell the licensing, but we have technology to forward your existing on-prem licensing to the cloud so you can seamlessly access it just like you could on a laptop or a workstation. We could also access licensing as a service, which all the major CA vendors are now providing, so we can tap into kind of licensing that exists out on the cloud, things like power on demand, other types of similar technologies that all the major ISVs now are providing. So that was a great question, but yes, we don't sell, we are the Swiss in that regard. We support, we will help you though access your licensing. Next question was, does this use InfiniBand? So InfiniBand is a technology that lets you scale out jobs to many, many cores and still get speed up as you add more and more nodes. So on AWS, they have a similar technology called EFA, and you saw the benefits from the previous slides from Rick and Erica that you can scale out to thousands of cores and you're still getting nice linear speed up because of EFA. But I think, Yanesh, I might have you tackle a little bit more of the details on EFA there for the audience member that asked that.
Yeah, sure. So EFA, or Elastic Fabric Adapter, is a network device that you can attach to your Amazon EC2 instances that will help you bypass the kernel for fast network communication. The EFA uses libfabric, so you can use any of the MPIs in your code that support libfabric out of the box. What EFA does is, like, EFA takes the busy work of moving packets out of the kernel and puts them on the EC2 Nitro card, which then takes the responsibility of slicing and dicing data and then pushing it out. Now, in comparison to this, like for InfiniBand depends on packet latency. So because it has to pick a path, which needs to be the fastest path, and then put the packets across it, keeping an eye out for performance degradation or let's say packet drops. So EFA doesn't have to do that. Like, EFA doesn't fixate on the order of packets that arrive. EFA takes the whole payload of data that the MPI or even like NCCL code wants to move, and then sprays all the packets across all pathways all at once. So this is what then enables us to see the type of scaling that Rick showed in his examples and get, like, yeah, almost like close to linear or even super linear scaling. Rod, does that help to answer the question?
Yeah, I think that was fantastic. And in fact, yeah, we were using EFA with the Hpc6a to scale out those Fluent jobs that Erica was running. So yep, great. Thanks, Yanesh. Next one was asking about now that you have the cloud, how do you what is the workstation role in your environment? So maybe Erica, you could tackle, like, what do you feel like now that you have this cloud access as the workstation? What is that that's still a workhorse, or what are you going to do with your workstation now, I guess?
Yeah, totally. I think we have a bunch of different uses for our workstation still. First, probably smaller jobs that we don't necessarily need the cloud for will still run on our workstation. We also, I didn't talk about it, but we do a good amount of ANSYS FEA, so now the workstation will be freed up for that. And then if it's not being used for smaller jobs or FEA, we have some data science models that I think can be sped up on our workstation too, just running our Python code there. So they'll probably still be pretty busy.
Okay. Yeah, I mean, a lot of people like to still post processes with it and do, have lots of other tools that maybe not always available on the cloud workstation. So, okay, great. And then somebody asked, what are the best applications for Hpc6a? So maybe we'll hand that, I mean, it's definitely CFD, but we'll hand that to Rick. Maybe Rick, you have some feedback on, best apps you've seen running on Hpc6a.
Sure. So typically it's jobs that we would refer to as tightly coupled. So these are classic CFD codes, sometimes the explicit or implicit finite element codes, in particular nonlinear ones, LS Dyna, Abacus, those sorts of things. the classic CFD codes, Fluent, CFX, Star CCM Plus, OpenFOAM, and others. You know, those will run best on these applications, and they tend to be, you know, quite large models with quite lengthy times to compute. So well suited for Hpc6a. We've got other offerings under AWS that may be better suited for you know, simulations that we refer to as embarrassingly parallel. So these tend to be found in the realm of biogenetics and molecular sciences and material and composite studies and things of that nature at the molecular level. So great question. Thank you.
All right. Well, I think that was the questions we have here on this session. If you have an additional one, certainly ask in a chat. We'll try to get back to you an email once we receive that. Usually there's a small delay before it sends it out. But I wanted to say thanks again to all of our speakers today. Thanks again to Accelerate Wind for taking the time to tell everybody about their journey to the cloud. And we look forward to seeing you on a future event.